Welcome! We are about to do a deep dive into C programming. In this explainer, we're going to build a solid foundation, starting right from the ground up with C's most powerful and sometimes feared feature, its direct control over computer memory.
So here's our game plan. We're going to start with the absolute core concept of pointers. Then, we'll see how arrays and strings are really just clever applications of that same idea. After that, we'll look at where variables live and for how long, and finally, we'll jump into the data structures that let you build truly complex and efficient programs. Okay, let's get into it.
All right, first up, the big one, pointers. Look, mastering pointers is pretty much the key to mastering C itself. They're not as scary as they seem. At their core, they're just special variables that hold memory addresses.
Let's make this crystal clear. You know how a normal variable, say an integer, might hold the number 5? Well, a pointer to that integer doesn't hold the number 5. It holds the location, the specific address in your computer's memory where that 5 is stored. This is the secret sauce. This direct access to memory is what makes C so incredibly fast and powerful for things like building operating systems or high-performance game engines.
So using a pointer is always a three-step dance. First, you declare it. You tell the compiler, hey, I'm making a pointer and it's going to point to an integer. Second, you initialize it. You give it an actual address to point to. And third, you dereference it. That's the magic part, where you follow that address to actually read or write the data you care about.
All right, enough theory, let's see this in practice. We're going to walk through this little piece of code line by line so you can see exactly how declaration, initialization, and dereferencing all work together.
Okay, check this out. We use the ampersand, the AND symbol. You can just think of this as the address of operator. It's like asking the computer, hey, where in memory did you put my candy variable? The computer gives back that address, and we store it inside our pointer, P. Just like that, P is now officially pointing to candy.
Now we see the asterisk again, but here it has a totally different job. It's the dereference operator. When you put it in front of a pointer like this, you're telling the program, don't show me the address that P is holding, I want you to follow that address and tell me the value you find at that destination. And since P is pointing to candy, the value it finds is, of course, 5.
And this is where you see the real power. By putting P on the left side of the equals sign, we're not changing the pointer. We're using the pointer as a remote control to go back to the original candy variable's location in memory and change its value directly to 10. See? When we print candy itself, its value has changed. Pretty cool, right? This whole idea has a huge impact on how functions work in C. By default, if you pass a variable to a function, you're just sending a photocopy. The function can mess with the copy all it wants, but the original is safe. But if you want a function to be able to modify the original data, you don't send a copy. You send a pointer. You give it the actual memory address so it can work on the real thing.
Okay, so now that we have a feel for pointers and memory addresses, let's talk about arrays. Because as you're about to see, arrays and pointers are very, very closely related.
So what is an array? Just think of it as a reserved block of memory, like a row of connected townhouses. Each element lives right next door to the previous one, with no gaps in between. This idea of them being contiguous, all together in one block, is absolutely fundamental.
Here we're declaring an array to hold 5 integer scores. Now, the golden rule of arrays in C, and many other languages, is that they use a zero-based index. This is super important. It means the very first element is always at index 0, the second is at index 1, and so on. So scores 0 gets us that first score, 90.
And here it is. This is the big aha moment that connects arrays and pointers. The name of the array itself, the variable scores, doesn't actually hold all 5 numbers. It just holds one thing, the memory address of the very first element, scores 0. It basically acts like a special pointer that's permanently locked on to the start of that memory block.
So because the array name acts like a pointer, we can do math with it. But it's not normal math. When we say scores plus 1, we're not just adding 1 byte to the address. The compiler's smart. It knows scores points to integers, and integers are 4 bytes long on most systems. So scores plus 1 actually moves the pointer forward by 4 bytes, landing it perfectly on the next element in the sequence.
This table sums up the differences beautifully. Think of a pointer like a reprogrammable TV remote. You can make it point to your living room TV, then your bedroom TV, but an array's name is like the label that's glued to the front of the living room TV. It's fixed, it can't be changed. And this changes how the size of operator works too.
Size of a pointer tells you the size of the remote control itself, but size of an array tells you the size of the entire TV. All right, let's take what we know about arrays and apply it to one of their most common uses in C, handling text, or as we call them, strings.
Now this is an absolutely critical point. A C string isn't just a bunch of characters. It's an array of characters that must end with a special character called the null terminator. It's literally just a zero value, written as escape 0. This little guy is the signal that tells functions like printf, okay, the string ends here, stop reading. Without it, you have chaos.
When you need to get input from a user, you have to be careful. The classic scanf with a %s is a bit of a trap because it stops reading as soon as it hits a space. So if you type John Smith, it only gets John. That's why the preferred function is fgets. It's much safer and does what you'd expect. It reads the entire line of text, spaces and all.
Because strings are just character arrays, C gives us a whole library of functions to work with them. You've got tools to get a string's length, which just counts characters until it finds that null terminator, a function to safely copy a string from one place to another, and one to tack a string onto the end of another one.
Okay, so we know how to create variables and pointers and arrays. But now let's ask a different question. Where do these variables actually live in our program, and how long do they stick around? This is all about scope and storage class.
So you've got two main neighborhoods for variables. Local variables are temporary and private. They're born when a function starts, they live only inside that function, and they're destroyed the moment the function ends. Then you have global variables. They're permanent residents. They exist for the entire time your program is running and can be accessed by any function, which sounds great, but can actually be pretty dangerous if you're not careful.
These storage classes give us even more control. Auto is just the default for local variables. You almost never type it. Extern is for globals. But the really interesting one here is static. A static local variable is a bit of a hybrid. It has the lifetime of a global variable, it sticks around forever, but you can only see it inside its own function. This is perfect for when you need a function to remember something from the last time it was called.
All right, let's start putting these pieces together. We're moving on from single variables to organizing complex data. We'll start with the basic building blocks and then see how to combine them into our own custom data structures.
So everything you build in C, no matter how complex, is made from these fundamental types. You've got int for whole numbers, float and double for decimal numbers, use double if you need more precision, and char for single characters or symbols. Remember, you can always use the size of operator to check exactly how much memory these take up on your machine.
Now, we take those basic types and build bigger things. We've already covered arrays and pointers. The next really powerful tool in our belt is the structure, or struct. This is a game changer. It lets you bundle different data types together to create a new, custom type that models a real-world thing like a person or a car. Here's a perfect example. We're defining a blueprint for a person, saying that every person will have a name, which is an array of characters, and then age, which is an integer. Then, in our main function, we create an actual person variable named p1. We can then access the individual fields inside it, like p1.age, using a simple dot. It's all about keeping related data neatly packaged together.
Okay, time for the final section. We're going to explore advanced, dynamic data structures. These are built using the pointers and structs we just learned about, and they are absolutely essential for solving really complex programming problems.
So what's a linked list? Well, remember how arrays have a fixed size? Linked lists solve that problem. They can grow and shrink on the fly while your program is running. Each element, or node, holds some data and, critically, a pointer to the next node in the chain. This makes them incredibly flexible for things like managing a music playlist where you don't know how many songs you'll have.
Next up is the stack. The perfect analogy is a stack of plates. You can only put a new plate on top, and you can only take a plate from the top. The last one you put on is the first one you take off. This last in, first out, or LIFO behavior is used everywhere, from how your program manages function calls to how the undo button works in your text editor.
Trees are exactly what they sound like. They're for representing hierarchical data. Think of a family tree or the folder structure on your computer. A really common and useful type is the binary search tree, which keeps its data sorted. This sorted nature allows you to find an item in a huge amount of data incredibly fast.
And finally, we have graphs, which are probably the most flexible data structure of all. They are perfect for modeling any kind of network where things are connected to other things, from your network of friends on social media to the map of roads your GPS uses to find the best route.
So here's the main takeaway. There is no single best data structure. The choice is a huge design decision that affects everything. You have to ask yourself these questions. Is my data linear or is it a network? What will I be doing most often? Searching, adding, deleting? How important is performance? Picking the right tool for the job is what it's all about.
Learning to weigh these trade-offs, balancing memory, performance, and the kinds of operations you need is what separates a good programmer from a great one. The real skill is to analyze the problem first, and only then pick the data structure that fits it like a glove.